All right. Hello, guys. Okay. This video is going to go along with your climate change notes. So they should look something like this. Some of you might have an electronic copy. So if you're virtual learning, I think I'm decided to give you a paper copy, or sorry, Google Doc. And then if you're in class, I decided to give you paper, this unit. Anyway, so we're starting our climate change unit. I usually just kind of do maybe a week or two on climate change. I think I've decided it's kind of important to at least touch on because it is such a politically charged topic. You can turn on, like not that long ago, you could turn on the presidential debates and it was mentioned. So what I think is missing in for so many people is, including like a lot of the teachers in this building, let alone your families, the people you work with, your friends. I think a lot of the science is kind of overlooked. I think no one really takes the time to kind of dig in and read the science behind climate change. So my hope is that after listening to these notes that you'll kind of be inspired either to maybe have a different take on, like the evidence of climate change, but also maybe even like look into it a little bit. So I do know that climate change, even just a few years ago was kind of like a controversial topic to bring up in a science classroom. But nowadays, honestly, it's just not even considered to be very controversial as far as the scientists are concerned. There is just so much scientific evidence that it's just kind of an accepted concept. And really a lot of the focus now is, okay, yikes. So this is happening. And what can we do moving forward? So one of the things that kind of gets brought up, and even like when I was taught about global warming, when I was at Fairmont High School, of course, we called it global warming back then. One of the first things that was really on everyone's radar was the warming factor. So global warming explains like a long-term increase in global temperatures. And again, that was like the first thing that really raised the red flag. So holy moly, how long ago? Oh my gosh, almost 20 years ago, I was at Fairmont High School learning this, and I very much learned like the concept of warming. Since then, and maybe so in like the last decade, scientists have understood that the threat is not just the warming aspect, but like all of the various changes that we're now seeing. So we now try to use the term climate change because it's much more accurate for the effects that we're seeing here on planet Earth. I try to use climate change. You'll probably hear me slip a time or two calling it global warming, but I very much understand that in fact, the things that are most threatening are just like the variety of changes, not just temperature changes. So climate change explains a much broader range of changes. So including rising sea levels, shrinking glaciers, accelerating ice melt in various places we'll talk about today, shifts in flower and plant blooming times, and just so many things. So anyways, we're going to take a look at all those things a little bit closer. I also like to point out that when I make my presentations, like every other unit, I make them on my own, 100% of them, but all the other units I use are textbook, various sources from the internet, Google Images for a lot of the images. And when I first made this presentation a few years ago, I tweak it every year, but I really wanted to be able to kind of show and prove where I got my data. So there's lots of numbers, there's lots of graphs. I want you to know that they are not from Google Images. In a few of them, I'll show you. I'll even point out they are from Google Images, but like the numbers that I have in this presentation are actually all from the NASA or NOAA website. So those are government agencies. They're funded by the government. They work with many other scientific communities around the entire globe with other countries, which I think is really valuable. So I wanted you to know that the graphs and everything that I've used in the presentation, I very intentionally only pulled from these well-supported scientific communities. So I think most of it actually is from NASA. But anyways, and quite literally, you can see if you go to their website, like NASA has an awesome climate change kind of section to their website. And that's kind of the framework behind this whole presentation is from their website on purpose, like intentionally. Okay. So first of all, let's talk about the causes of climate change. Right, you should have already done the greenhouse effect gizmo. And the whole point of that is I wanted you to understand what the greenhouse effect is and also the importance of it. So here obviously is an image of the sun, and here's the earth. And I'm going to call this kind of like hazy region around the earth, the atmosphere. So within the atmosphere is what we have the greenhouse effect, right? So the gases that make up our atmosphere retain or release a particular amount of heat from the sun. And it's actually so perfect that we depend on it being so perfect. The gases that make up our atmosphere are the reason why we have life on Earth. All the other planets have a very different atmosphere, and that's why they don't have life on Earth life on the surface of their planet. So you can kind of see here what I'm trying to show is that sunlight is, of course, emitted to the surface of the Earth, and then it can do a couple of things. It can leave the atmosphere, so a lot of it appropriately leaves the atmosphere. And then a lot of it is absorbed by the gases in our atmosphere, and it's kept right here within our atmosphere. And that balance must be perfect. And again, that is kind of what we rely on. So we rely on the very perfect balance of those gases. And one of the things, so within those gases, so here's Earth in the middle. And then in this little chart on the left is Venus and Mars. So those are the planets that are closest to us, right? On either side of us. So, and you can see how drastically different that gases that make up these three planets' atmospheres are, right? So look at carbon dioxide. The Earth's atmosphere has about 0.03% of carbon dioxide. But holy moly, look at Venus. It's like higher than 98% of the atmosphere on Venus is carbon dioxide, right? Those are drastically different. We could keep on going and looking at the gas composition of all these differing atmospheres, and you can see how different they are. So some scientists even call this the Goldilocks effect, right? So we don't want too much, we don't want too little, it must be just right. This balance, when we tweak this balance, this is where we're beginning to see problems. So there are 4 major gases that are contributing to the greenhouse effect. These 4 gases are the ones that we also see having changed over recent decades. So the first one we'll look at is water vapor, literally water. Yes, water occurs naturally in the atmosphere, but what we're seeing is an increase in water vapor. So the levels are currently increasing because of warmer temperatures. So just like when you take a hot shower, you guys can imagine that warmer temperatures allow for more water to evaporate in the gaseous state. And then that causes more cloud cover. So actually what we see with cloud cover is if you imagine sunlight radiating to planet Earth, but there's cloud cover, it actually reflects more. So some people actually think that increased water vapor is not natural, but it actually may decrease the effects because it may reflect more of the sun's heat than before. So actually water vapor is changing, but we aren't totally concerned about the effects of that just yet. But that is one factor that's changing. Another one is nitrous oxide. So if you look at the chemical equation here, or the chemical structure, you can see that this is a nitrogen molecule. Sorry. Nitrous oxide is released into the atmosphere from using fertilizers. So we know that pretty much everything that we grow is doused with fertilizers multiple times a growing season. Everything that goes into our clothing, our paper products, our obviously our food and drink, right, is grown somewhere with lots of fertilizer. Burning fossil fuels, we do that every single day for the electricity, for the lights that are above my head right now, but also my sweet minivan that I drove to school today. So we burn lots of fossil fuels. And biomass burning. So biomass burning is just burning of stuff. Now, we don't do a ton of biomass burning here in the United States, but other countries, they literally still burn, like wood or other plant matter for heating and cooking. Right now, humans account for about 40% of the nitrous oxide in the atmosphere. So that's a lot. So we currently have released a lot of extra nitrous oxide. I forget what order your notes go. Oh yeah, methane. Okay, so let's hop over here to methane. Ugh. So methane, you can see in the chemical structure of methane, it's just a carbon and hydrogen molecule. It is released from the decomposition of waste. So a lot of that decomposition comes from, or methane comes from landfills. So you probably are familiar with the huge landfills down in Moraine. So there's two massive ones very close to us that are constantly releasing methane into the atmosphere. We are trying to tap into that because we can burn methane. So you may have also heard about the possibility of capturing the methane. And some landfills are capturing the methane and then using it actually to like source electricity in their region. Okay, so landfills release a huge amount of methane. Rice paddies, literally growing rice. Again, here in the United States, not very common, but other countries and cultures, that's one of their largest, like pieces of agriculture is growing rice. Rice is grown, I actually don't know much about it, but rice is grown in, they're called paddies, but their farm fields go through like intervals of being flooded with water and then being drained. And the nature of the flooded fields inhibits a lot of, I should say, decomposition, and those critters release methane into the atmosphere. And then the other one is the meat industry, literally cow farts. So we are raising, I should say, so many cows for your hamburgers. That is one of the leading causes of like releasing greenhouse gases into the atmosphere is our meat industry, and it's cow farts, a huge percentage. So methane is the most harmful greenhouse gas as far as retaining heat goes, but it isn't as near as abundant as carbon dioxide. So the last one here is carbon dioxide. Again, this is the most abundant gas that we're releasing as humans, according to our lifestyle. So carbon dioxide is naturally released by respiration. So we know that every time we breathe out, we naturally release carbon dioxide. And respirating organisms like humans and most animals have been doing that naturally for years now. So it's not necessarily like the breaths that we're counting and concerned about. The other place that carbon dioxide is naturally released from our volcanoes. So volcanic explosions release a lot of carbon dioxide. The concern here is the next bullet point. So we're mostly concerned with the carbon dioxide that's being released from deforestation and burning fossil fuels. So fossil fuels release a huge amount of carbon dioxide into the atmosphere, and our lifestyles have increased with the amount of carbon dioxide or fossil fuels that we're burning. So we're driving more than ever before. We're buying more crap than ever before. We could take an entire period to think about the amount of carbon, or I should say fossil fuels, that is burned just to make the stupid paper wrapper that your McDonald's hamburger comes in. So if you imagine a McDonald's hamburger tonight, you might have for dinner, imagine all the fossil fuels that went into making this hamburger. Not only the cow, right? All the fossil fuels to make your little beef patty, but also all the stuff that like producing the mustard, the ketchup, the pickle. I mean, it's actually been over 20 years since I had a McDonald's hamburger. I don't know what's on a McDonald's hamburger. But all the stuff that goes into making your one little hamburger patty, and then it's wrapped conveniently in this little paper wrap that you use for about 1, maybe 5 minutes of your life. And then we throw it away to a landfill where then it's going to be broken down and release methane. So this whole process, this whole lifestyle that we live, I say almost everything you do in your day requires fossil fuels to be burned, right? So that is the largest concern here. The other thing I mentioned was deforestation. So obviously you can imagine, I forget because it changes and I'm not good with numbers, but a huge amount of trees, specifically even just the rainforest, like many, many acres every single day are still just being clear cut down. Well, imagine those many, many acres every single day, how many tons of carbon dioxide they naturally pull in, right? So through the process of photosynthesis, we used to have a balance where, yes, the organisms on Earth are breathing out carbon dioxide, but you know what? Those plants are pulling it in. And it truly was perfectly balanced. So now that we are not only releasing more carbon dioxide into the atmosphere, but also now we're cutting down the organisms that, that pull in and bank carbon dioxide. Now we're seeing this huge off balance. Okay, so that's the gaseous part of climate change. So this graph is from the NASA website. So in 2013, the daily level of carbon dioxide in the atmosphere surpassed 400 parts per million for the first time in human history. The last time levels were that high was about 3 to 5 million years ago. So as far as humans have lived on Earth, as long as we believe that humans have lived on Earth through lots of different types of scientific dating, scientists believe that the carbon dioxide has never been this high in the atmosphere. So here you can see that obviously the data goes way back in time. And here we are today. So you can see just exactly how high that actually is when you look back in time at the values. Okay, so have humans caused this, right? That's the big question. A lot of people uneducated about climate change would say, this is natural. The atmosphere on Earth has gone through many changes. Yes, 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 yes. But what I think is most valuable is to understand that, and this slide is wordy, I try not to do this, but the intergovernmental, meaning basically like lots of different countries, panel on climate change, a group of over 1,000 independent scientific experts from countries all over the world concluded that there's a more than 95% probability that human activities over the past 50 years have warmed our planet. So again, this is just one example of, like, the scientific community is not flustered trying to figure out what has caused this. It's actually pretty simple, and it makes sense when you look at our daily lifestyle. Okay. So now let's look at evidence. So what types of evidence do we see for climate change? The first one in our notes is just global temperatures rise, right? So that's kind of the one that, again, has raised flags in the past. The planet's average temperature has risen about 2 degrees Fahrenheit. Is that in your notes? No, sorry, you write it on another slide. About 2 degrees Fahrenheit rise already. This change has been driven largely by increased carbon dioxide and other human-made emissions like the other gases we just talked about. Most of the warming has occurred in the past 35 years. So that's like in my lifetime. So really starting, scientists rose the red flag, and then just in my little lifetime, now we are understanding and we see the reality and the warming. So with 16 of the 17 warmest years on record occurring since basically year 2000. 2016 and then just last year tied for the warmest years on record. I'm going to skip that video, I think. Okay, so I think this is so valuable. I got this from the NASA website again, but I think it's really important because this shows, so here we are 2020, so here we are current, and then we go back in time to the year 1880. And if you notice, there are 4 lines on this line graph, and they're from 4 of the top or major scientific organizations across the world. So NASA is obviously United States. And NOAA is another one in the United States, and you can see the other 2. They all have their own sets of data of temperature and climate data. And so here what they've done is plopped all of their numbers to try to compare what they've seen. And you can see that starting from 1880 and moving forward to today, you can see that actually their lines match up pretty darn well, right? I think that's so important that yes, scientists all over the globe are working on this data. They're tracking this data. They're comparing the same numbers. And by golly, you know what? They actually are all seeing the same thing. So you can see that the temperature anomaly really just means like the temperature change. And so you can see the significant increase in temperatures over the last, 100 or so years. Okay, evidence for climate change again is warming oceans. So the oceans have absorbed much of the increased heat. So with warmer air temperatures, they increase heat. The top 2,000 feet of oceans showing a warming of about 1/3 of a degree Fahrenheit. Now that seems so tiny, or like the 2 degrees Fahrenheit in the atmosphere seems so tiny, but we'll look in a little bit about, we'll look at some of the specific effects of just a few degrees. We're also seeing shrinking ice sheets. So Greenland and Antarctic ice sheets have significantly decreased in mass. We see this we don't even have to look at scientific numbers. Frankly, we can look at pictures. And I'll show you some pictures in just a second. NASA's data showed that Greenland has lost 30 to 60 cubic miles of ice per year. And then Antarctica lost about 36 cubic miles of ice within just a few years. And that trend is just continuing, and they're just continuing to melt. So here's a picture of Greenland. I actually got this from a scientist that I saw talk on climate change, almost 10 years ago. And he got this data from NOAA. So it is actually outdated. So you can see on the left here, this is a picture of the ice on Greenland in 1992. This is using satellite imagery. And then on the right side, this is 2005. And you can still see the drastic change. So imagine what it looks like now, 15 years later. So our very own Glacier National Park is obviously known for the beautiful glaciers. This is, I searched and searched. This is from Google Images, and I got it from a New York Times article ironically just had this. I liked the comparison here. So you can see this was a picture way back from 1913 and then in the same spot in 2012. And you can see how much of the ice has melted. And this is just one spot, one little tiny dot in really on the globe of ice melting. Glacial retreat. So glaciers are retreating almost everywhere around the world, which is basically on, glaciers melting. So we're seeing significant melt. Here was an estimate of the ice in about 2000, and then estimated back over 100 years before, and you can see how much larger they believe that glacier was. We also see decreased snow cover. So satellite observations reveal that the amount of spring snow cover in the northern hemisphere, which is us, has decreased over the past 5 decades, and that snow is melting earlier. So we see that as like one red flag that yes, temperatures are warming, so it would make sense that we have less snowfall and that snow is melting earlier. We'll kind of get back to that in just a second, where it may actually be a good thing for some people. And then we see sea level rise. So we're already seeing sea level rising because of a couple of different reasons. We're seeing the global sea levels already rose about 8 inches in the last century. And the rate in the last 2 decades, however, is nearly double that of the last century. So what we mean to say is that the sea level is rising, and it is rising faster and faster and faster every single decade. I think we're going to watch a video in class, and it shows you like a coastal town. I think it's the city manager is interviewed, and he's just talking about like, holy moly, I mean, their infrastructure, their plumbing, the like houses, businesses, everything. I mean, everything's just being flooded every single day, and he'll talk about it, but I mean, it's happening. These coastal regions are already being affected by this increase in sea level. So one of the causes of increase in sea level is obviously flooding the current infrastructure. So anything that's built close to or near the current shores are a lot of them are already being flooded or greatly affected. One of the things I think is interesting also is that organisms, like in this picture, I'm focusing on plants. So plants are going to have to try to migrate inland, right? So if you look at the top picture now, the shoreline plants live in this really specific region, right? So they love sandy soils. They live right there. If you've ever been to the beach, there are plants that live specifically right here, right along the natural shoreline. If this sea level just continues to rise, they'll get flooded and washed away, and their populations may be decimated. But what we're actually seeing and hoping for is that some plants will quite literally migrate inland. So as organisms don't survive, they're flooded and they die here in the current, like now they get flooded out. We're hoping that some plant species are actually able to just, like the seeds are going to be planted inland, and the seeds actually are able to survive. The problem is in this little image, you can imagine that here it kind of works because there was nothing there, but there's roads. There's a lot of coastline is just covered in housing or restaurants, right? So unfortunately, we're not very hopeful about these particular ecosystems being very resilient. Okay, so here is, this is from NOAA. And so this is the projected change in sea level after ice from the Arctic completely melts. So, and they think they estimate that will be totally melted by 2050, which is not very far away. So this is Florida. here's current Florida. I want you to pay attention to the current coastline. Okay. And then again, I'm going to go back a slide. Remember what they anticipate actually happening after the Arctic melts, which is melting at a very high rate. And again, within our lifetime, they think that will be melted. So here's Florida now. Watch the screen. Here's Florida now. Here is Florida after the Arctic is totally melted. I'm going to go back and forth a few times. Oopsie, sorry. So pay attention down here. Watch now how much of that huge chunk of Florida is flooded totally underwater. We could even go back up here. I think that's Louisiana. Is it terrible? I mean, I should know that. Watch that landmass, right? Just totally covered. They also did the same projection for Shanghai, China, because they also have really low elevation. So projected change in sea level after the same amount of ice. So the Arctic ice melts, which again is they expect to be in about 30 years. So here is Shanghai, China right now. And here is what they anticipate to be underwater in 30 years. It is estimated also that this region that's flooded includes about 40 million, or the homes of 40 million people. Okay, we also anticipate, so here's kind of where the change comes in, the term climate change. We just anticipate lots of extreme events, and we're also starting to see them. So for example, the number of record high temperature events in the United States has been increasing, while the number of record low temperature events has been decreasing. So, so temperature changes, intense rainfall events, wind events, extreme storms, extreme droughts, floods, all of these things are, wildfires is another big one. There's tons of concern about the future for wildfires. They've also already grown in the frequency and then the severity of the wildfire events. I'm going to go back. What's I going to say? I don't know. Okay. So here, what they're tracking here, this goes up to 2014. And what they're tracking is they've kind of like made a bar graph of all 4 of these types of events together. So drought is gray, extreme temperatures, that could also be even really cold temperatures, flooding events, and wildfires. And you can see just the increase since you guys were born, right? Compared to back here when I was born, the significant increase in just like what we call extreme events. Keep in mind that these extreme events are oftentimes happening in the same location. So one season, a farmer might be dealing with the most severe, the most frequent floods while he's trying to grow a crop. And then the next season or the next year, he may be dealing with the most severe long-term drought, right? So it's not even like farmers just need to deal with more drought. No, they're also being dealt with floods just the very next season or the next year. Okay. We're also seeing within our oceans, ocean acidification. So since the beginning of the Industrial Revolution, the acidity of surface ocean waters has increased by 30%. So this is the result of humans emitting more carbon dioxide into the atmosphere, and then it's being absorbed by the oceans. So basically when the oceans absorb more carbon dioxide, it actually reacts with molecules in the ocean and creates an acidic molecule. So the amount of CO2 absorbed by the upper layer of the ocean is increasing by about 2 billion tons per year. One effect that we're seeing is, we're seeing critters be affected by the increased pH levels of the ocean water. And one of the things that seems to be hit the hardest, as far as what I've seen, is the little babes, the little ones. So this is a pteropod, and it's a shelled organism. So normally inside this shell, there'd be a little, I mean, it looks like a snail, right? So it's a marine, essentially a marine snail. And this is a tiny little baby. So they start growing, and they're so beautiful and tiny, but you would maybe think it's like just a little tiny rock. That's how tiny they are. And their little shells, you can see at 0 days, they're so tiny and paper thin. They're like literally translucent. You can see through them. These organisms, for example, tend to be the most susceptible to living in more acidic waters. So their shells just don't have the, they're not protected enough. So, and this is just one example. So another thing that are being affected are like the tiny little baby fish, and any other organism in the ocean tends to be more affected by what we're currently seeing at the younger age. So what we could anticipate unofficially in my brain is that, in a decade or two, we're going to actually see populations plummeted, because starting like nowish, fewer and fewer babies are surviving every single year. And warmer waters. So we kind of mentioned that, but yes, so we see an increase in, so climate change is affecting coral reefs. This has kind of been a hot topic probably the last couple of years. So you've probably seen things about this, but yes, so the coral reefs are dying, literally just dying out at a huge rate. One of the causes is the warmer waters. So a coral itself is basically two little critters living together. So it's a photosynthetic algae, and then basically like an animal species. So an algae and an animal, and they live within the coral structure, and they live together. But the problem is with the warmer temperatures, the algae is dying. So, and the algae is what provides the food and provides the color, and it's dying. So then the coral itself dies. So you can see the picture. This is from Google Images, because I wanted like a kind of like a before and after. So you can see here on the left photo, this is the coral reef before, and then this is after. And this is on the far left, you can see an image of just a dead coral species. And so we call it coral bleaching, just because the algae has died, and so it leaves behind this white skeleton. Another reason that we believe coral reefs are dying is because of the ocean acidification. So because of the increase in coral reefs tend to be in shallower waters. And so the shallower waters are where we're seeing temperatures warming the most, and the water decreasing in pH, which is increasing the acid basically. So anyways, here's another before and after of our poor little coral reefs. Another effect of climate change is just increased global temperatures, which I kind of mentioned at the beginning. So we currently see already a 2 °F increase in global temperatures. What we expect to see is an increase of up to 10 degrees in the next century. And again, I know 2 degrees sounds like nothing, but we'll take a look at what the heck is already happening with a 2-degree increase in temperatures. So when we think of organisms, it's kind of the Goldilocks effect again. So organisms, whether it's a plant in your backyard or a coral in the coral reefs, organisms have what we call a zone of tolerance. So I love this graph. This is just from Google Image, but I love it because it shows this is where organisms are going to be most abundant. This is their optimum range. Let's think of temperature. It could be the pH of the water they're living in. It could be so many things, but let's just focus on the temperature where these organisms are living. So this is their optimum range, and this is where their population is going to be the most abundant, the largest, right? If the temperatures decrease, just a little bit, that puts them in what we call the stress zone. So some are going to be surviving, but they're feeling stressed. Some will die off, but their population still exists. So this is where they're stressed. This could be animals, this could be plants. If we continue to decrease the temperatures, this is what we call the zone of intolerance, and the organisms die off. The same thing is going to happen if we increase temperatures. So now let's say we increase the temperatures a bit, and again, we're in a stress zone. So organisms are feeling stressed. Some are dying off, some are going to survive. And then if we increase the temperature even more, that is again where we get to the zone of intolerance, and organisms cannot survive. Right now, we are seeing a lot of organisms, even right here in Ohio, in the stress zone already. And we think I actually just saw, I should have made you guys watch it. It was a couple local field biologists talking about the stress that climate change is already putting on our local amphibian species. So things like amphibians are about 10 years ago started to show the effects in the United States because amphibians, like frogs and salamanders, their skin is typically like moist, and they appear to be more susceptible to susceptible to like hardships in surviving with increased temperatures. One of the reasons I saw was there's actually an algae at warmer temperatures, and algae grows on their skin and kills them. And that is one example of an effect of climate change that people don't think about, right? People are like, well, a frog can survive to a 2-degree temperature change, but we're actually seeing, across like populations of organisms, strange effects that most people wouldn't think about. And we'll look at some more today. Another effect of climate change is that organisms are going to be forced to adjust their range. So it's kind of weird for us to think about, but we're talking plants or animals literally moving, because if they're, let's see, how could I explain this? If an organism has adapted to live in, let's say the average summer temperature, let's just say 70 degrees, it's totally off the top of my head. If we're seeing an increase in temperature like we are, it's warmer. So there's two things that they can do to try to find a place where, again, the average would be 70 degrees. They can either move away from the equator, or they can move higher in elevation. So let's look at this map. This is actually from NOAA as an example, but so this is Tennessee. Okay. Nope. No, this is Tennessee. Okay, so we're in Tennessee. We're looking at elk. Okay. Let's just imagine that their preferred temperature, off the top of my head, was 70 degrees, which I know isn't true. Let's just say 70. Temperatures are increasing. Elk can either move north a little bit, maybe into Kentucky here, right? So they're going to move north where the new temperature average would be 70 degrees, and maybe they could find habitat and make the move and survive. Another possibility in Tennessee, which is why I picked Tennessee, is there's some Appalachian Mountains, right? We got some mountains there. So they can also move a bit higher up in elevation to, because what we see is temperatures decrease as we go up a mountain. And maybe they could survive there. But there's a whole different set of plants that live there, other animals. So it's not just as easy as elk moving their population up in elevation or altitude, latitude. But this is all what we're kind of speculating, is that plants and animals may actually shift their current habitat. Again, we're seeing varying effects in plant and animal populations. One of the examples I already told you was like frogs growing algae on their backs because of increased temperatures. Some other specific examples are changes in the actual animal behaviors. So we're seeing organisms mating earlier, changes in migration, eggs hatching earlier, a disruption in predator-prey relationships. And we'll look at some specific examples right now. Again, it seems like you wouldn't really care, but let's look at some examples. So let's see, Fowler's toad, this exists in the eastern US, and they've been shown to breed an average of about 6 days earlier over the last 10 years. Just bear with me, listen. The little penguin here, he's from Australia, and they have showed that they were laying eggs an average of 9 days earlier over the last decade. Let's see. Oh, a red-backed shrike. So they live in Europe and Western Asia, and they migrate, and they arrived an average of about 3.5 days earlier in the spring. This little red admiral butterfly lives in the temperate regions of Europe, Asia, and North America, and they emerged as an adult butterfly an average of over 15 days earlier. So there's lots of examples of this, right, where organisms over the last decade or two, probably at this point, have now shown a change, a significant change by like a number of days in these types of things. So like when they're laying eggs, when their eggs are hatching, when they're migrating, when, and let me show you an example of why we care. So here's an example with just a generic bird, a migratory bird, and then caterpillar hatching. So let's imagine we're in Ohio and it's 1980. Okay, so this was 4 decades ago. If we look here, we're at May 1st, and April 25th is peak bird arrival. So here in Ohio, whatever bird this is migrates in, and their peak arrival day for decades has been April 25th. So they're coming in. They're moving into Ohio. They're spending days and days staking their claim for habitat, finding a mate, building nests, and so on. What we then see happen about June 3rd in Ohio is peak bird hatching. So the little baby birds are hatching, and it perfectly correlates to caterpillar season. So caterpillar hatching season. So now you guys, this is something that has evolved together now for how many years? But in Ohio, typically we would have seen on June 3rd up in the treetops of Kettering, Ohio, little baby birds hatching and peak caterpillar hatching, right? So that is perfect because the mama birds and dad, I should say, a lot of dads help. They're going to fly around those treetops, grab the caterpillars, and feed them to their young. So that is a very balanced, expected predator-prey relationship. The problem is what we saw in about year 2000 is one of those organisms is being affected by a change in climate. So we see peak bird arrival a little bit earlier, but we also see the caterpillar season, the peak caterpillar hatching is happening before the birds hatch. So here's what's happening. Within the 10 days now, when the peak caterpillars hatch and then the birds hatch 10 days later, the caterpillars have already literally died, been eaten by something else, or moved on to the next phase of their life. That's how quick some of these organisms shift their phase of life. So then we have the baby birds are going to starve to death, and their populations after 5 to 10 to 15 years, we're going to say, oh my goodness, why is this bird population plummeting? And we can look back and say, oh my gosh, it's their food source. So this is one example of why we actually care if an organism is 5 days ahead of schedule, 5 days behind schedule, because it makes a significant difference in the big picture. Okay, I'm going to try to pause it for a sec. Okay, Sorry about that. Here we go. All right, so what do we expect? Temperatures we expect to just continue to rise. We expect the frost-free season and then the growing season for farmers to lengthen, actually. So this kind of goes back to even like the decrease in snowfall and snow melting earlier, kind of ties into actually like a longer frost-free season. So potentially this could help farmers. Now, it doesn't mean that the native organisms, the plants and the animals, are going to adapt well, right? But one kind of positive piece of the puzzle is some people anticipate that farmers will actually be able to like lengthen their growing season by a number of weeks. I'm gonna just keep going. So changes in precipitation patterns. This again comes to where the term climate change comes from. So again, in some areas, we're seeing increased rain, increased drought, decreased snow, and increased snow. And sometimes it's the same spot, sometimes it's the, it's not the same spot. So basically, we're just seeing changes depending on the location. We're seeing more frequent and much more intense hurricanes. We're already seeing this. We're seeing stronger winds on average and a lot more rainfall along with these hurricane events. We expect the sea level to rise 1 to 2 feet by the year 2100. So, and that's a lot. That's extremely significant in these coastal regions. Again, remember that global sea level has already risen by 8 inches. We saw that already. This comes from ice melting and the expansion of the water molecules. Lots of flooding to be expected in the future. We believe that Arctic ice melt is projected to continue, and it's just going to continue until it's totally gone again, which is in about 30 years. So on NASA, they had it broken up. You could like click your region. So I just clicked the Midwest, and then it had according to our region, what we should expect. And so I thought it was kind of interesting. So NASA says that for here in the Midwest, US Midwest, we should expect to see extreme heat, heavy downpours and flooding. The flooding will affect infrastructure, which is buildings, sewage systems, health, agriculture, forestry, transportation, air and water quality, and more. Climate change will also exacerbate a range of risks to the Great Lakes. The reason I think they kind of included the Great Lakes is because we've said a lot about the oceans, and I would imagine that the Great Lakes is feeling a lot of the same changes. So again, one of the statistics that I kind of say over and over and over again is I think it's so important to realize no matter who you spend your days with, who you share your space with at home or at work or at play, that 97% or more of our actively publishing climate scientists, so like actively publishing means that they're currently collecting data and analyzing data and drawing conclusions based on that data, 97% or more of climate experts agree that climate change is happening and that it's extremely likely that humans and their lifestyles have caused it. So this to me is why this is not even debatable. It's not controversial. It's happening. So the scientific community understands this. The last thing here is what are we going to do about it? So there's kind of two things. There's mitigation and adaptation. Number one, mitigation is actively trying to reduce climate change. So this involves reducing the flow of heat trapping greenhouse gases into the atmosphere by either reducing the release of the gases or increasing where we can collect them, where they collect. So we call them like carbon banks. For example, a forest absorbs through photosynthesis literally tons of carbon dioxide from the atmosphere. So the importance of planting trees, for example, would be an example of mitigation. So basically reducing climate change. Not only increasing carbon banks, for example, but also trying to change our lifestyles to decrease the gases that we're emitting. There's lots of ways that we can try to mitigate the gases that are released because of the way that you live your life. And that's basically everything you do, literally. The food that you choose to eat, the clothes that you choose to wear, the crap that you choose to buy, the amount that you choose to drive, what you choose to drive. Right now in your room, how many, or classroom or wherever you are, I guess, how many things are turned on when they could be turned off. So lots of things about a lot of choices on your daily lifestyle would come back as mitigation. And then adaptation. So adapting to life in a changing climate. So we realize that there are changes. And so this involves adjusting to actual or expected future climate. So being a bit realistic and realizing that this is not stopping. It's just, if anything, is going to continue, right, for definitely the rest of your lifetime. And so what can we do then to adapt? So one of the pieces of this puzzle you'll see in the video is coastal communities are being very realistic, and they are writing grants. They're trying to get grant money. They're increasing taxes for the citizens that live there in order to build a sewage system that isn't going to be flooded every single day. Literally moving structures, right? So moving homes, or trying to anticipate what could help reduce the stress of changes depending on where you're located on the globe, basically. Okay, and I think that is it for climate change.